Hello everyone and welcome back. Let's continue our discussion from the last video. In the last video, we learned about convergence and divergence. Well, actually we look at certain pictures of some sequences and pictorically we learn what convergence and divergence means, right? But the problem is that when a sequence is given to you can't always use a picture to determine convergence and divergence. I mean, you can, but to do that, you have to draw your sequence, which is an inconvenient way to decide the convergence or divergence. So in this video, we are going to learn a proper mathematical way where we can use it to find convergence and divergence of a given sequence. Alright, now let's talk about convergence and divergence again. Think about an example sequence where the sequence is 1 over n, where n values are going from 1 to infinity. This is an infinite sequence. Now, to decide whether the sequence convergent or divergent, what we have to do is we have to look what happens to the sequence eventually, right? We look at the tail of the sequence. That's what we did in the last video, right? We didn't care what happens to the sequence in the beginning, but what happens at the end or eventually, well, there's no end, but what happens to the sequence eventually for large values of n, that's what we use to decide the convergence and the divergence, right? Now, how do we express this mathematically? Now, when I'm saying what happens to the sequence eventually, I can represent that mathematically when I say let n goes to infinity. Now, when I let n goes to infinity, n means the position of the sequence. So you're making the position of the sequence goes to infinity. That means you're looking at larger positions of the sequence, okay? Millionth term, trillionth term, billionth term, likewise, okay? So you're looking at what happens to the sequence eventually, okay? So by letting n goes to infinity, I can talk about the sequence, what happens to the sequence eventually. Now, to talk about convergence, we want to know where does the sequence approach eventually. Now, how are we going to represent that mathematically? Well, we can say, okay, to see where does the sequence approach eventually, we can take the limit of the sequence when n goes to infinity. So limit of 1 over n goes to infinity. The meaning of this whole thing is that I can condense down into a one sentence. Where does the sequence 1 over n approach when n goes to infinity? Or where does the sequence 1 over n approach eventually? That's what it means by taking the limit of the sequence 1 over n when n goes to infinity. So what's the limit? So when n is getting large, the denominator gets large. That means the whole fraction gets really small, right? So this is approaching to 0. So the limit is 0. And actually we can say this sequence is convergent to 0 because eventually the sequence will get really close to 0. Okay, now the whole idea in this lesson is that if you want to know whether a sequence convergent or divergent, just take the limit of that sequence. Okay, now if your limit is a finite real number, okay, then your sequence is convergent. That means your sequence is approaching to a real number, right? Okay, that's what it means to be convergent. Right, let's take another example. So let's think about the example 1 minus 1 over n. We already discussed about this sequence in the last video pictorically. Okay, n values are going from 1 to infinity. Now let's take the limit because that's what we need to do mathematically to find the convergence, right? Or convergence of the sequence. Now think about this. When n goes to infinity, we know 1 over n approaches to 0, right? Limit of a constant is constant. Limit of 1 is 1. 1 minus 0 is 1. So the limit is 1. 1 is a real number. So hence this sequence is also convergent. So both of them are, let me just write CONV for convergence. So both of these sequences are convergent sequences. Okay, all right, now let's look at some divergent sequences. Just two couple of examples and we'll be done with this video. My next example is, let's see, n square. Now, if you think about the sequence n square, okay, where again n values are going from 1 to infinity. Now, if you take the limit when n goes to infinity, n square, now when n becomes large, n square becomes even large, right? So, the eventually what happens to the sequence is that it goes to infinity, right? The limit of this sequence is infinity. Now, this is not a real number. Infinity is not a real number. So now, because of that, this sequence is divergent. Okay? Right. Now, before we summarize, let's take another example. So how about negative n square? So if you take the limit when n goes to infinity of negative n square, now it goes to negative infinity, right? The limit is negative infinity. Again, this is another example of a divergent sequence because negative infinity is again not a real number. The last example that I want to give you is the sequence. We already saw this negative 1 to the n. Now here, in this sequence, if you take the limit when n goes to infinity, limit of negative 1 to the n. Now, negative 1 to the n means sometimes it's 1, then it's negative 1. 1, negative 1, 1, negative 1. So it's switch between 1 and negative 1, right? Eventually, that's also what's going to happen. 1, negative 1, 1, negative 1. So it's neither approaching to 1 or negative 1. Okay, this sequence doesn't approach to a real number, one real number, and it doesn't approach to infinity or negative infinity either. Okay, so this sequence is special. Now, first of all, be clear on your head that this sequence doesn't go to infinity, right? Because it's switching between 1 and negative 1, not going to negative infinity either, but it's not going to approach to a real number either. Okay, so the limit does not exist in this case. Okay, still this is divergent because limit does not exist means this sequence is not approaching to a one real number. Remember, it has to be unique. Limit has to be unique. Okay, it just need to be one number. You cannot say limit is 1 and negative 1. No, it has to be 1. In this case, there's no limit. So another divergent example. Okay, so in nutshell, when you want to decide whether a sequence is convergent or not, just take the limit. Now you can run into two scenarios when you take the limit. Okay, first scenario is your limit is a real number. Let's call L is a real number, any real number. Then your sequence is convergent. Okay, if the limit exists as a real number. Now if your limit is infinity or negative infinity, or if the limit does not exist, then unfortunately your sequence is divergent. Okay, right? So if you want to decide whether a sequence is convergent or divergent, take the limit of the sequence when n goes to infinity. Great. Now what we have to do for the rest of this video series is that we have to take different types of sequences and we have to learn limit taking techniques, because sometimes you get trigonometric functions or rational functions. Like, I mean, the sequence is represented by like a rational function or like a trigonometric function. So various kind of weird sequences, you get various kinds of weird sequences, and we have to learn limit taking strategies, techniques, and those type of things. That's what we are going to do for the rest of this video series. We are going to look at different types of sequences, but the idea is same. You take the limit, you see whether it's finite or infinite or it does not exist to decide the convergence and divergence. All right, hopefully it makes sense, and in the next video we'll look at a different type of a sequence. Thank you very much.